Okay, now we'll talk about dynamic data. So after watching the pointer lecture, hopefully you're starting to understand the mechanics of how pointers work. But you may be wondering, well, why in the world do we have pointers? It seems like we're adding this extra step of indirection that we never needed before. We were certainly able to write many programs without pointers. So what is the value in using pointers? Well, the answer is they allow us to access a special section of memory called the heap. And we use heap, the heap, to create dynamic data. Okay, so in the pointer lecture, I mentioned this idea of a process image. This is what is in memory when a program is running. Okay, so if you have three programs running on your machine, you have maybe a browser, a word processor, and an IDE. Each one of those programs has a process image, which is basically just the representation of that program in memory. Okay, so let's look at a process image in a little more detail. Let's kind of blow this thing up here. Okay. Every process image is made up of 5 sections. So we have this one section is called the text section. This is basically this is where your compiled code goes. We have this thing called a process control block. We have a section for global data. We have a section for this thing called a stack. And we have a section for something called the heap. So this is a process image. Okay, every single running program has these 5 sections. So the compile instructions, the text section, that comes directly from our code. So the compiler looks at our code and it turns it into machine instructions, and those machine instructions get put in the text section of the process image. And the next section, the process control block, holds all kinds of accounting information about the process, like which instruction from the text section should the processor execute next. So in the PCB we have this thing that says, all right, the next instruction to execute is going to have this address. Okay. Now the global data section is used to store global data. Okay. So global data is accessible from anywhere in the program. Every single function has access to all global data members. However, making all of your data global is probably not wise. Right? Some data is sensitive, like salaries or medical histories. You don't want every single programmer to have access to that. One might accidentally or maliciously change that data. So it's a good idea to limit sensitive data to just a few programmers. So let's look at a program here that has some piece of global data. So here I've declared global num outside of any function. That makes it global. And then it is accessible anywhere in the program. Inside main, inside func. Every single function has access to this global piece of data. Okay, global data also sits in memory for the lifetime of the program, even if it's not being used. So some programs, like those on our cell phones, for example, they run 24 hours a day, 7 days a week. If they all use global data, we might run out of memory, especially on a phone that probably has less memory than a normal laptop or desktop computer. So let's look at this code here. So let's say we had, if z is greater than 0, we're going to do something, and we need this integer called x to help us do it. Okay, let's say we do some other interesting things here. Otherwise, if that's not true, we'll have some float called y. going to do something interesting with that. Okay. What's interesting here is we don't need both x and y to be in memory because only one of these branches is ever going to get executed. So it would be a waste to have both x and y sit in the global section of the process image for the entire lifetime of the program. All global variables reside in that global data section of the process image. So the text section, that's compiled code. The process control block is accounting information. And the global section of the process image, that's where global data resides. The next type of data we have is called local data. And local data is accessible from the point of the declaration of that piece of data until the ending curly brace of the block it was declared in. And then the data goes away at the end of the block. Okay, so we've all used this kind of data as well. So here we have, again, a main and a function called func. And inside func, we declare this thing called local num. So it is available to use from this point on line 19 to line 22. Okay, because this is the ending curly brace of the block that this local variable was declared in. Now, another name for this kind of data is stack data. And this is because the stack section of the process image is where these local variables go. And before I talk about that, notice up here, this code would actually not compile, right? Because I have the reference to local num. This should definitely be commented out, or I should not be able to access local num inside this block because it wasn't declared there. It's only accessible from here to here. Okay, so back to this idea of a stack. A stack is it's a data structure. We're actually going to be talking about what a stack is shortly. But basically it's a last in, first out container. And that means the last item added to the stack will be the first thing that's removed from it. Okay, so if we had a stack, if we had this container, and we're going to add the items 1, 2, and 3. Okay. Well, when we push the value 1, push is that's what we say when we want to add something to a stack. The stack would look like this, and then when we push 2, the 2 would go on top, and when we pushed 3, the 3 would go on top. So it's called a stack because you could kind of imagine like a stack of trays or something being put on top of each other. Now, if we wanted to remove things from the stack, okay, because we always removed the last thing that was inserted, we would get these items back in the order 3, 2, 1. So we added them in this order. We're going to get them back in basically the reverse order. Okay. Now, a process's stack is used to remember where to jump back to after a function has been called. So in other words, when we call a function, the location of the function call is pushed on the stack, and then the flow of control jumps to the function. When the function ends, the program looks at the top of the stack to determine, well, where are we going to jump back to? Okay, so I could write this little program that looks like this. We'll have a main, and we'll call print name, and maybe do some other stuff. And print name will call two other functions. Maybe print first. And print last. And print first will just print my first name. Print last will print my last name. Okay, so we have this thing called a call stack. Okay, so we know every program starts in main, and whenever we come to a line that has a function call in it, okay, we store the address of where this function was called, and then the flow of control jumps down here, and we start executing statements inside print name. Okay, so this is some address in main. This is the call stack. Right, and here we happen to call another function. Right, so we're going to store the address of this call. This is somewhere inside print name. Right, we're going to push that on the stack, and then the flow of control is going to jump down here. We're going to see out my first name, and when we come to this ending curly brace, that's when we go back to the call stack and say, all right, well, where are we going to jump back to? Whatever address is being stored here, that's when the flow of control is going to jump back here, and we're going to start going sequentially to our next statement. Our next statement happens to be another function call. So imagine this value is removed from the stack, or it's popped from the stack. So the call stack would only have one item in it. But now that we're calling print last, again, we would push the address of this function call, which again happens to be inside print name, onto the stack. And then the flow of control will jump down here. We'll print out my last name. When we come to the ending curly brace, we'll pop the stack. So this is going to tell us where to jump back to. That'll be right here. And then when we come to this ending curly brace, we will pop the stack again to get the address in main where we're supposed to jump back to. And then again, we'll go with our sequential flow from there. Okay, so that's what the stack section of a process image is used for, is to kind of keep track of where we're going to jump to and return from. Now, along with the return location, all variables declared in a function are also placed on the stack. So when one returns from a function, the call stack is popped, and all of the variables that were declared in that function, since they are also pushed on the call stack, and we're removing something from the call stack when we come back from a function, all of those variables go away. And this is also true of actually every single block of code. Okay, if I have some code that looks like this, let's say I'm in some block of code somewhere, and I have, if something is true, well, then I'm going to declare this variable maybe called x. Maybe we'll do something with x. Okay, but when we come to the ending curly brace of that block, okay, at this point, x is no longer on the stack, because at every curly brace, the stack is popped, and all the variables that were declared within that block are gone forever. Okay, so to compare global data and local data, we see there are actually limitations to both. Global data occupies memory for the lifetime of a program, and it's accessible by all the programmers. Local data is only in memory for a fixed amount of time, and that the amount of time is really dependent on the structure of the code. So where the curly braces are determines how long a local variable is in memory. Now, dynamic data, that's the subject of this lecture, is accessible for exactly the amount of time that the programmer wants the data to be in memory. Okay, this type of data is new to us. You've probably never used dynamic data before. The programmer controls when the data goes into memory and when it is removed. The memory that this type of data is allocated from is called the heap. Okay, and that's the third data section in the process image, the others being the global section and the stack section. Okay, so let's look at the heap. You can think of heap as just this big chunk of memory, and every byte inside the heap is either free or being used. Okay, So here's our big chunk of heap space, and right now let's say it's all free. When a programmer creates a piece of dynamic data, the operating system looks in the heap for a large enough chunk of data and returns the address of that chunk to be stored inside a pointer. So if we ask for 10 bytes, we have to go find 10 bytes that aren't being used for anything else. We'd have to mark those as being used. And then what we would do is we would return the address of that chunk, okay, to be stored inside a pointer. Okay, all data on the heap is unnamed, so you can't assign a name to any chunk of data on the heap. The only way to access it is with a pointer. And this is why we're learning about pointers at all. All of our complex data structures are going to use this heap because it's so much more flexible for us as a programmer. Okay, the way programmers allocate data on the heap is with the keyword new. Okay, so if I want a piece of dynamic data for a float, okay, I would do something like this. So when the flow of control gets here, the new keyword says go look in the heap for room for a float. Okay. And then what's going to happen is, again, the operating system is going to go look for a free chunk that's big enough to satisfy the request, and it's going to mark that chunk as being used, and it's going to return the address of that chunk to be stored inside some kind of pointer. So we might do something like this if pnum is a pointer. Now you can also declare an array of elements on the heap, also using the new keyword. So if I want 5 floats, okay, the syntax looks like this. This says, again, go to the heap. New always means go to the heap, and find room for 5 floats that are all right next to each other. Allocate all of them as being used, and then return the address of the very first byte of the very first element in the group. That's going to be stored inside a pointer. And then the way programmers deallocate or free data is to use the the delete keyword. So the way this works is you again, delete is a keyword, and you would give the name of a pointer. So this says, go to what this pointer points to and mark that section as being free. Okay. And if we had an array of data, we would use we'd have to use these empty square brackets. So the delete keyword, an empty set of square brackets, and a pointer that points to a chunk of data. So if we called this, I don't know, if this was some kind of pointer, float pointer, then this would delete the chunk of 5 floats that are sitting on the heap. Okay, and the best way to understand this, I think, is to look at some code and to draw a picture. So that's exactly what I'm going to do here. Okay, with program 10. Okay, so starting out here we have a struct data type. We have the student data type that has an ID, a mid, and a final. And we have a main, and inside main we call this function called dynamic memory. And when we come back, we're going to probably do some other useful stuff and even more stuff here. But we're going to look inside this function called dynamic memory. Okay, so what do we do inside here? Well, we declare some variables. So let me draw my memory. Okay. Now remember, we have 2 types of memory available to us now. We have stack or local data, and we have this heap space. Okay. Well, these 3 variables, p dynamic number, p student, and p array, those are stack variables. How do I know that? Well, there's no new keyword. So anytime we create a variable inside a function and we don't use new, well, those are stack variables. Okay, and their types, they happen to be an int pointer, a student pointer, and an int pointer. Okay, so this, we'll call this one p dynamic number. Create another one called p student. And we'll create another one called p array. Okay, so 3 pointers, 3 local variables, 3 stack variables, which happen to be pointers. Okay, right now they have garbage values in them. We'll fill them in a second. Okay, our first step is we're going to set p dynamic number equal to the result of asking for room for a new integer. Okay, so again, new is a keyword. It should show up in some highlighted color depending on your IDE. So when the flow of control gets here, this says go look for room for an int somewhere on the heap. So let's say, well, here's room for an int, and we're going to return the address of that int to be stored inside p dynamic number. So this is going to point right here. And now we can use the pointer, we can dereference the pointer to store a value inside that chunk of memory. So we have the value 10. Okay, next we say pStudent is equal to the result of requesting for a new student object. Again, when the flow of control gets here, we're going to say go find room for a student, which we know is made up of these 3 data members. And the address of this chunk of memory is going to be returned to be stored inside this pointer called pStudent. Okay. Now we could use our arrow notation to access the object on the heap. So we'd have 1, 90, and 100. And we can also ask for, in this case, an array of 10 integers. So again, when the flow of control gets here, this says go on the heap and look for room for 10 integers. Okay, so we'll have an index value from 0 to 9. And the address of the very first one of these is going to be returned inside p array. So notice p array, its type was just a pointer to a single int. And in fact, that is exactly what it is. Right? When I had p dynamic number was just a single integer, p array is pointing to an array of integers. Their data types are exactly the same because, like we talked about before, an array is really just a pointer to the very first element in an array. Okay, so at this point our memory looks like this. We can, of course, now march through this array of 10 elements, and we could use our array notation, or if you really wanted to, I suppose you could use the pointer arithmetic notation, but this is basically just going to put a value in each one of these. So I think we're going to use I to put a 0, a 1, a 2, all the way up to 9 inside the boxes. Okay, so this is what our memory looks like right now. Okay, we've allocated 3 pointers, we've allocated 3 chunks of data on the heap. Now that we're done with it, it's up to us, the programmer, to decide when this memory should go away. So we're done with it, we need to get rid of it. Okay, and this is where the delete keyword comes in. This says delete pStudent. This says go to what pStudent points to. So pStudent points to this chunk of memory right here. And the fact that we're deleting it says we're going to give that back. We're going to mark this chunk as being free. Okay, so this chunk of memory can now be used for later allocations. Okay. And then notice what I do here. I set pStudent equal to null. Remember, null is our special value of 0. That means the pointer doesn't point to anything. Okay, and null is not a keyword, but there is a constant declared, which basically holds the value 0. So you can either use all uppercase null or the number 0. I sometimes do one or the other. Okay, the next thing I do is I'm going to delete the array. So if you ever have a pointer that points to an array of stuff and you want to delete it, you have to use the empty square brackets here. This says go to what parray points to. Parray is here. It points to this whole chunk of memory here. Okay. This says free this up. Okay, and this chunk of memory might be used for other things. Okay, for future other parts of the program might want to allocate some memory, and now these two chunks will be free to be used. Okay, now we come to the ending curly brace. That means the flow of control is going to jump back to main, and this is where we're going to do some more useful stuff here. And of course, whenever we jump back to a function, all the local variables go away. So p dynamic number, p student, p array, those are now gone. So we've freed up these two and we've gotten rid of these three local variables. You can see clearly there's a problem here. I forgot to delete the chunk of memory that p dynamic number was pointing to, and that's kind of a big problem. That's called a memory leak. Okay, so when you're working with dynamic data, we have to look out for a couple things. The most important being a memory leak. Okay, so memory leak is when a piece of data is on the heap, but there are no pointers pointing to it. It occupies memory and it can't be used for anything. It can't be freed. Eventually, you could exhaust all of your heap space with repeated memory leaks. Okay, so let's kind of pretend we called dynamic memory inside a loop, many times. Well, every single time we call that, we're leaving an integer on the heap. And at this point, if we imagine none of these things existed except this chunk of memory here, every single time we call the function, we're eating up room for this integer that we can't use and we can't free. We can't delete it because there's no pointers pointing to it anymore. Okay, so I'm told that if you start like a Windows 95 machine and just let it run without doing anything to it, in about a month, there's so many memory leaks in the operating system itself that the whole system crashes. It just runs out of memory and the whole system crashes. So you have to avoid memory leaks at all costs. We programmers are very good at remembering to allocate data on the heap when we need it. We're not so good at remembering to delete it when we're done with it. And this would be an example where the program might work fine for a while because I allocated the data when I need it, I used it when I need it, but when I was done with it, I forgot to deallocate one of these. Well, again, if you have a lot of memory, I suppose that your system might be able to survive that. But if you don't have a lot of memory, these memory leaks could consume your entire memory. And when you run out of memory, that's your system tends to crash then. That's a very bad thing. Okay, so we're good at remembering to allocate data. We're not very good at remembering to delete it. Almost all modern programming languages, except C and C++, have a mechanism to monitor the heap space and to look and see when there are memory leaks. And when there is a memory leak, this mechanism will automatically free those chunks of memory. And this is called a garbage collector. You might have heard of a garbage collector. What I love about teaching this course in C++ is that there is no garbage collector. And you, the programmer, actually have to think about not only when you allocate, but when are you supposed to deallocate. Okay, and I think that's a good exercise to do at least once in your programming lives, is to really be forced to think about, when you need to allocate and when you need to deallocate. Okay, the other thing to look out for is this thing called a dangling pointer. So a dangling pointer is when you have a pointer that holds the address of a piece of data that has been deleted. And using that pointer would be a mistake. So after a piece of data has been deleted from the heap, the pointer that points to it still holds a numeric address where that data used to live. However, the chunk of memory might have been allocated for some other variable, so you definitely don't want to use the dangling pointer. Okay, so let me draw a picture to explain this. Okay, so let's say we had a program that does something like this. Again, we have kind of our stack space, our local variable. Pint is a local variable. And then here we're asking room for an int. And the address of that int is going to be stored inside pint. So pint points to this chunk of data. All right, and we might do something with pint. Dereference it. And store the value 10 in there, let's say. Okay. And then when we're done with it, of course, what we would do is we're supposed to delete pint. Okay. So again, this says go to what pint points to, and then mark that as being free. So if some other part of the program needs access to some heap space, well, now this 4 bytes, that's available for use. Okay. And then let's imagine, well, yeah, somewhere else in the code, somebody asks for an array of, say, 3 floats. Okay, so this says, all right, well, now we're going to have p array. And if we get really unlucky, what might happen is p array might point to this chunk of memory, which is all totally and completely free. And we might use the array. So we could zero out all the values. Okay, so we put a 0 there, a 0 there, and a 0 there. Okay, but notice pint is still around. It still holds the address of this chunk of memory that no longer belongs to us. Okay, this is why we call it a dangling pointer. If I were to accidentally still use the pointer, if I say star pint is equal to 20, this says go to what pint points to. So right now pint points right here, and right over these bits here, and put the value 20 inside that chunk of memory. Okay, and clearly we can see this is bad. Your code might work. You, the person using pint, might work, but the person who's using the array, their code is definitely not going to work. They're expecting these 3 things to have 0, 0, and 0, and now for some reason we have 0, 20, and 0. And they're going to look at their code and try and figure out, well, what in the world is going on? It's really not them at all. It's you using this pointer that really doesn't belong to you anymore. That memory doesn't belong to you anymore. Okay, so after you delete a piece of dynamic data, you should always set the pointer to null. Okay, this way at least the program will crash if you use a dangling pointer, and you'll know where to look for the problem. So what I should have done here, after I deleted pint, I should have set pint equal to null or 0. And now what would happen, okay, at least now the program will crash. That's actually a good thing, because what was happening before was somebody else's code just wasn't working, and they had no real idea where or why that was happening. And in fact, if they ran the program again, if the array didn't happen to land in exactly the same location as it did last time, well, the program might work fine until, again, we get really unlucky and the array just happens to land where that int used to be. Okay. Now at least we know, right, if we dereference a null pointer, the program will crash and we'll have an idea of where to look for the problem. Okay, so these are really important things we always have to look out for: memory leaks and dangling pointers. And like I said, almost everything we do, every data structure that we're going to look at is going to use the heap, is going to use dynamic data. So it's very flexible. It's the great thing about it is the memory is allocated for exactly as long as we want it to be allocated. We just have to be careful that we use it correctly.